Eliminate all forms of PIM from the SP core. Man, people are never nice to PIM. Welcome back to the MVPN video series. In this video, we move into a new realm that was previously untouched in our videos, and that is the concept of MLDP in-band signaling. So, let's begin. So what exactly is this in-band signaling, and what differentiates it from, I guess, out-of-band signaling? Well, the RFC that defines the solution has some pointers. So in-band, using the opaque value of an MLDP FEC element to carry the S(G) or *G identifying a particular IP multicast tree. And overlayers, out-of-band signaling protocols such as PIM and BGP are used to establish the mapping between an LSP and the multicast packets that need to be forwarded over that LSP. But to really understand these terms, it's important to revisit our MLDP concepts one more time and just see what these things really are. So, what do we have in MLDP? What constitutes MLDP? We obviously have multipoint LSPs, and then what identifies a multipoint LSP? Well, very succinctly, it's two or really three things. Number one, it's the root of the LSP. Number two, it's the opaque value of that LSP, so the FEC opaque value. And if you want to consider number three, that would be the type of the multipoint LSP, whether it's point to multipoint or whether it is multipoint to multipoint. Considering this, it's important to realize how can we get our multicast packets, the IP multicast packets, the C multicast packets that we have to switch. How do we get them to use these multipoint LSPs? The process formally is called mapping. And how we have done that, for example, in profile 1 that we covered, or MDT-mLDP, was in two separate but distinct ways. First, we had an emulated LAN. So this emulated LAN was between all of the PEs in that MVPN, and a multipoint to multipoint LSP was then provisioned to provide the multicast services within this emulated LAN. So once it was provisioned, how were the multicast packets mapped to this MP to MP LSP? How are we telling them that this is the LSP that you should be using? These are the particular labels. Well, remember that little thing called the VPN ID? That was, if you remember, crucial in provisioning the LSP since it provided the structure of the opaque value, which is extremely important. So that leads to another question. How did the PEs obtain this VPN ID? Do you remember? It was manually configured. So we went into the VRF and we manually configured the VPN ID. So putting two and two together, we were basically manually mapping the multicast packets in that VRF to that LSP. Okay, but secondly, there was also the case of the data MDT. So we've just defined the default MDT, but there was also the data MDT. We were essentially mapping specific S(G) states to specific LSPs. Well, this time, the source side PE, yeah, that's a real term that I just made up right now. The source side PE, so the PE behind which the source sits, created the mapping. Remember, once the threshold of the packets, the bandwidth of the packets exceeded a certain threshold, then it created this new mapping. And once again, it used the VPN ID as the base of that mapping. It just increased the suffix. And then it multicasted this information via UDP onto the other PEs. And for this, it used that MP to MP LSP, or the emulated LAN, if you will. So therefore, it can be said that the mapping was somewhat manual because it's using that manual VPN ID data that we have supplied it. But the signaling of that LSP was UDP based, right? So we used UDP to signal it. Keep this in mind, right? Because it will be crucial in about a minute here or so, maybe two. So you may also know from other experiences that BGP can be used for the same purpose. right? So BGP can be used for this mapping. In fact, that solution is the most scalable solution of all the MVPN solutions available, and I promise you it'll be a topic of many of our future videos. So, well, you have UDP, you have BGP, and they can both be used to signal the mapping, and you can always manually map. So now let's get back to MLDP, and more specifically, let's get back to the MLDP opaque value. Remember that this opaque value, firstly, is of arbitrary length, right? It can be of any length as long as we define that length and share it in the packet. Secondly, it does not have a specific structure. It could be gibberish, it could be anything. So what that essentially means that its structure is really determined by the LSR that programs that value inside the FEC and the LSR that decodes it, right? So those two. Now, these are usually PEs in our MVPN. Right now, we're just talking about two, but you can scale it to multiple PEs, but they're always going to be the PEs, the edge LSRs. But the length and the structure format of this value have a greater consequence. And that consequence is that almost any information can be coded into this value. And as long as these edge LSRs, these PEs, understand the meaning of that value, they can decode this value, then this scheme just sort of works. So remember, it's called the opaque value for a reason. It's called opaque value because it means almost nothing to the P routers. As long as it matches that opaque value with the route and the type of the LSP, they just basically signal it forward, but they don't understand what it really means or what is it supposed to mean. So they just create the forwarding states, they switch the packets along, and they're oblivious really to the greater design. So now, before I go back to the aspect of in-band versus out-of-band signaling that I started talking about eons ago at this point, let's talk about signaling in general first. And I promise you I'm coming to the crux of this in a second. Especially, let's talk about signaling when it comes to multicast. Signaling essentially really is the act of informing the other multicast routers what type of multicast flows would a router wish to receive from them. So, right, you're signaling to the other multicast neighbors what sort of multicast flows do you have state for? What sort of S, G would you like to receive traffic for? What sort of star, G would you like to receive traffic for? Well, and when you think of signaling, think of PIM join prune messages. So if you're well versed with PIM, which I'm assuming you are, think of the PIM join prune messages. So they carry this signaling, the state information, and they help create proper multicast states in the MRIB, sort of multicast routing tables or state tables of the various routers. So that's how you exchange this signaling information. Now, since we can carry this information, specifically the information that the joins carry, so the star, G, the S, G, if you think about the structure of the opaque value, we can carry this information in the MLDP FECs themselves. So that brings me to another question. Can we not use MLDP for the signaling as well as the mapping? So we're already using MLDP for the forwarding, but because of that structure of the opaque value, can we not program this S, G right inside that opaque value? And that would tell, number one, the signaling, right? So what sort of states do the two routers wish to receive? But number two, mapping. What sort of traffic should be mapped, right? So if it carries the S, G, obviously you want to map the S, G traffic onto that LSP. It's sort of a 2-in-1. Well, the answer is, yeah, of course we can. And in-band signaling, that is exactly what we do. So like I promised, back to the crux of this piece. The reason for that long review was to explain in-band versus out-of-band signaling, like I said at the start. And here it is. Here's the difference. If the opaque value carries the S, G or the star, G information inside it as the FEC, then you're basically using MLDP for signaling the multicast states, i.e. the signaling is in band. Conversely, if you use another protocol, to signal these states and or to map these states to an LSP, such as you can use PIM or BGP or UDP, then the signaling is out of band from an MLDP point of view. And that is the major difference, in band versus out of band. Let's summarize this really quickly. So MLDP now in in-band signaling carries the C multicast states, and it carries them across the SP core. So the signaling really is in-band rather than overlain on top of the MLDP, so on top of that emulated LAN. The multicast state, the S, G or the star, G, is carried in the MLDP opaque value. And that is basically the gist of it, right? So let's proceed to the MVPN options. Now, these are the two that we have already taken a look at. We have looked at profile 0 and we have looked at profile 1. They both use that same concept of the emulated LAN. And we were basically overlaying C-PIM on top of the emulated LAN, whether it was GRE provision, whether it was MLDP provision. Well, now it's time to move on. So in MLDP in-band signaling, so this is also either profile 6 or profile 7, and there's a tiny difference between them. And I'll explain that later, but this basically, the diagram covers both profile 6 and profile 7. If you look at all of the aspects of it, everything is similar to profile 1. You have C-PIM working between the CE and the PE, your transport is MPLS, your core signaling is MLDP, so you're using core MLDP trees. But the major difference is the C multicast signaling now is MLDP. So there is no C-PIM now running between the two PEs. Shocking, I know, but because you can use MLDP to carry those states, you really just use MLDP for the signaling, i.e. once again, in-band signaling. So, and if you really think about it, the actual diagram sort of looks like this. So this is what I explained, and this is what the actual diagram looks like because you're doing this hop by hop. With C-PIM, because it was overlaid, it was only working between the two PEs, but the MLDP signaling has to be hop by hop. Now, given the Ps don't really understand what they are processing, but they are really still processing those states in a way. So they're creating those forwarding states and they're processing the states. So if you really think about it, it is going to be hop by hop by hop, and each P is going to be involved, even though they don't really understand what's happening there. So what are going to be the consequences of this? So number one, there is going to be reduced C-PIM activity on the PEs. So because there is no PE to PE C-PIM adjacency, you really have reduced traffic. You have literally no C-PIM traffic, no hellos, no BSR, no join prune, and this is going to have some repercussions, especially that BSR. But you have none of that now happening between the PEs. So really, the C-PIM is now disjointed, right? So the C-PIM is not continuous between the sites. It's C-PIM within a site, MLDP inside the SP core, and then C-PIM again at another site. Now, because of that BSR thing, I think, there is no official Cisco support for the any source multicast aspect of it. So any source multicast with the RP, etc., star, G, that's not officially supported by Cisco. Even though there's an RFC for it, Cisco doesn't yet support it. You can use a couple of hacks to make it work on iOS XR, but that's, again, unofficial support. I'll show you how to do this, but this is not officially supported. In the manuals, everywhere in the documentation, ASM is not supported. But in fact, what they say is SSM is the only thing supported. So I've only tested this in a lab environment and it works, but you have to use a couple of hacks. We'll discuss them. Now, unique point-to-multipoint LSPs have to be created for each multicast state. I repeat that, for every single S, G state. Remember, we're only supporting SSM officially here. So for every single S, G state, you would need a unique point-to-multipoint LSP. If you think about it, there is linear growth now of the point-to-multipoint LSPs as the CMCs grow. So as you have more customer states, customer multicast states, S, G states, the P2MP or LSPs are going to grow linearly with them. This, in fact, is a major drawback of this solution. Now, you can use ACLs to limit the traffic somewhat in in-band signaling. So what traffic can use in-band signaling can be covered with ACLs, but ultimately it's not really the most scalable of solutions. So having discussed the consequences, let's discuss the operation of this. So the operation of this is actually quite straightforward. If you followed along so far, it's not going to be the toughest thing. So in the solution, let's do a couple of, in the operation, let's do a couple of things at the get-go. So we will have the green, and that green depicts the C-PIM traffic. So this could be C-PIM or this could be IGMP traffic. In this case, it's IGMP because I have the receiver connected directly to the PE. But you also have the blue, and that is going to be the MLDP traffic, right? So to keep those in mind as you go through this. Now, the very first thing that happens, which is point 1, is that the egress PE receives a PIM or IGMP join for an S, G. Now, we were talking about profile 6 and profile 7. If this receiver, so remember, it's not all just VPN traffic, it could be just regular traffic as well, right? A customer that doesn't sit in a VRF, it sits in your global table. If this particular state is coming in a VRF, if you're receiving the signal inside a VRF, that is profile 6. So if it's VRF bounded, that's profile 6. If it's global or non-VRF, then it's profile 7. That's the only difference between them. There's going to be major differences in the SP core, but from the point of view of what profile 6 is versus what profile 7 is, if it's working in a VRF, it's profile 6. If it's working globally, it's profile 7. It's as easy as that. So you basically get to learn one thing and use it for two different things, if that works. So once again, the second thing now is going to be the VRF bound sometimes. So it's in traditional Cisco square brackets, that means it's optional. But essentially you're going to do, so this is an S, G, and actually I sort of messed up here. So let me back off on this. Actually, no, let's do this. So let's take that off, and I'm going to go with profile 7 again. So this here is still profile 7. Oops. So if it's VRF bounded, it's profile 6. Otherwise, it's profile 7. So now, from the top, you're going to receive a PIM or an IGMP join for a particular S, G. So this is for an S, G. What's going to happen next depends whether this particular interface here is within a VRF or it's not. But really doesn't matter. The process is exactly the same. And the process is that an RPF check is going to be performed on the S. And what you're trying to find from that RPF check is you're trying to find the PE that is the next hop for this S. So whether it's via an IBGP, a multi-hop IBGP, or whether it's via VPN v4 connection, doesn't really matter. Ultimately, you need a PE as a next hop that this source sits behind. So you do an RPF check to gather that information. Now the PE that is the next hop, so this particular PE here, that is the next hop. This PE becomes the route for the MP2MP LSP. So remember, for the MP2MP LSP, you need a route. You already know the type, so that's information portion 1. You need the route, so we have already determined that. And the next thing would be to create the opaque value. And how do you create the opaque value? You basically just create the opaque value from the S, G information. So you have the route, you have the MP2MP LSP, so this is 1, This is information number 2. This is information number 3. You have all 3 pieces of information that you need to start signaling a P2MP FEC. So, and basically signaling an LSP. So this leaf then starts that process of signaling that LSP with those 3 pieces of information. P is going to receive it. P is oblivious to the nature of it. It's just simply going to forward it on the shortest path up to the root. The root will now receive this. So now we are at number 7 because we've already done 6. We've passed the P router. Number 7 is the root PE receives this P2MP information, and it's going to install an S, G state. Now this is sort of nebulous whether you want to put it in green or whether you want to put it in blue, but ultimately this is a multicast state. Maybe it just should be a completely separate color because so far it's just a state. But what the root is going to do is it's going to extract that S, G information. So 7 and 8 sort of should be flipped, I guess, but it extracts that S, G information. It installs this state with this particular interface in the oil. And now it needs an ingress interface, an IIF, right? And that IIF is going to be the RPF interface towards this S, which in our case happens to be sort of directly connected. We are keeping it simple. But once again, I've moved back into the PIM realm because the root PE from that point on, beyond the SP core, is going to signal to S for this particular S, G via PIM. And this is exactly what happens. You have PIM coming in, you get that value converted into the P2MP FEC, you signal the FEC, you install the states everywhere where they need to be. And this could be multiple leaves doing it. So there could literally be another PE over here that is, or maybe call it PE3, that is signaling the same information. So maybe it has another receiver that sits behind it that needs the same sort of information. So whatever have you, this is going to be a multicast state. It's going to be a point-to-multipoint LSP. But the thing that you have to remember is it starts off at SPIM, it gets converted into MLDP in the core, and then it ends its life also as PIM. And once the traffic starts flowing in the opposite direction to the arrows, this is just going to work. So it's going to be IP multicast up until the PE, it's going to be label switch multicast between the PEs, and then it's going to be IP multicast beyond the leaf PE. Now that we've covered all of the basics for MLDP in-band signaling, it is finally time to have some fun on our iOS and iOS XR devices. We will be covering Profile 6 since, in our opinion, that is the more involved of the two, but I promise you that you will have enough of a head start to configure Profile 7 all on your own. But unfortunately, we have run out of time, so that becomes the topic of our next video. Till then, I would like to thank you for joining us and urge you to stay tuned for our next video. Thanks.